to our next chapter on amines, nitrogen containing compounds. Here are a few exciting ones: cocaine, nicotine, mescaline, and morphine. And they all have a nitrogen containing compound. We'll see here shortly that alkaloids is a fancy way of saying nitrogen compounds in plants, mostly synthesized by plants. Now, why are all these exciting? That's what DARE stands for, isn't it? Drugs are really exciting. Many drugs of addiction classified as alkaloids. It's this thing here, dopamine. That's why I go bungee cord jumping, right? Dopamine stimulates that pleasure center in the certain part of your brain. I want to say hippocampus or one of those brain pieces. And dopamine almost looks like some of those we saw there. Epinephrine. This is your fight or flight neurotransmitter. Something horrible is about ready to happen. Your body puts out a bunch of this stuff. You have superhuman strength. You can run. You can fight. So notice here's a L-tryptophan. Supposedly, when you eat all that turkey, what happens to you? Yeah, you feel a little drowsy. Tryptophan. If you take this off, I think you get serotonin, which dopamine and serotonin, two neurotransmitters. Here's one I don't like. Maybe I should like it. Histamine. How many of you like your histamine? You don't. You take an antihistamine if you have allergies. But it says it dilates blood vessels. Maybe I could cure my high blood pressure with hay fever. Niacin. So we can classify amines the same way we do carbon compounds, like primary, secondary, tertiary, and a thing called quaternary we're going to get to in a second. So one alkyl group on a nitrogen, we call that primary. Here's two alkyl groups, we're going to call that secondary. Here's three alkyl groups. Now there's no more room for any hydrogens to get our three bonds on nitrogen. If we get four groups, we're going to call it a quaternary ammonium salt. Four groups bonded to the nitrogen. You can see it has this positive charge. So when I say quaternary ammonium salt, normally there's a chloride, bromide, some anion. And here we might see some of these: cyclohexylamine, terbutylamine, N-ethylaniline, pepridine, N-diethylaniline. This might be foreshadowing some nomenclature. I don't even know how to pronounce that one. We'll just move on. So here are quaternary ammonium salts. The nitrogen atom has four alkyl groups attached. It puts a positive charge on the nitrogen. Acetylcholine, a neurotransmitter. If we back up to Redman's revenge, let's just back up for fun. Anything better to do? What's Redman's revenge? Maybe that's not politically correct. Western Europeans came over here and they took over the land. How'd the Native Americans get revenge? How many people does tobacco kill a year? Quite a few. So it turns out nicotine bonds to acetylcholine receptors in your body, in your nervous system. Where was that? Acetylcholine, a neurotransmitter. So your body has all these acetylcholine receptors that get acetylcholine, turn things on, turn things off. How many of you are in biochemistry? All right, so there's this receptor lock and key. It's a big thing in biology, but so these are all over your body, and the nicotine bonds to it strongly. Things aren't working. Your body grows more. The cells start putting out more of these receptors because they're not working as well. They're all tied up, latched onto nicotine, and that's the basis of a lot of things. Tolerance and withdrawal. You get so many receptors on your cells. It takes more and more of the amine to have its effect, and then you get all these receptors, and then you remove the amine and there's an imbalance. All right, back to quaternary ammonium salts. Suppose we could relate that back to drugs. Most of your drugs, read the label on the bottle. So a lot of times they'll say hydrobromide, hydroiodide. Well, not the quaternary ones, but we'll see. Why would an amine have that name? We'll get to that in a little bit. The nitrogen is positively charged. All right, common names. Common names of amines are formed from the names of the alkyl groups. That's why at the beginning of fall semester I say learn all your alkyl groups, serve you well, followed by the suffix amine. Cyclohexydimethylamine. Benzyl group, benzylamine, diphenylamine, ethylamine, diisopentalamine, diethylmethylamine, tetrabutyl ammonium chloride. So I guess now we're learning how to name a quaternary ammonium salt. Amines as substituents. We use amino, a molecule with a higher priority functional group. The amine is named as a substituent. So 3-amino, what's the number one? What's the high priority? The alkene. 1, 2, 3. So 3-amino, cyclopentene, double bonds understood to be at the number one. Carboxylic acid is way high in the priority group. 1, 2, 3, 4. 4-amino butanoic acid. So this would be IUPAC. This is an old common thing with the Greek letters. Gamma amino butyric acid. So once again, know your toluene, your aniline, your anisole, your phenol, benzaldehyde, benzoic acid. Because when you see one of, ooh, damn, is it making a liar out of me now? I would name this as an aniline derivative. Oh well. Do as I say, not as I do, or do as the book do when all those are wrong. A molecule, all right, let's keep going. IUPAC names. The name is based on the longest carbon chain. The E of the alkane is dropped and replaced with the name amine. 1, 2, 3, 4. So 1, 2, 2 butanamine. 1, 2, 3, 4. There's a substituent 3-methyl 1-butamine. Aromatic ones, you already know this as aniline. So notice they're naming this as a derivative, aniline. Orthoethyl aniline or 2-ethyl aniline. Something new, N diethyl. Normally we have those numbers out in front. So the letters N mean bonded to the nitrogen. N diethyl aniline. What's this or business? Here it's getting named as a derivative of toluene. Here it's being named a derivative of aniline. I guess I'd have to accept either on a quiz, right? Parent compound is called aniline. This is some weird common name. Good. This here's the IUPAC. We don't have to worry about that messing up our rules. Heterocyclic amines. Endo, here's an important one. You see it in biology. Purine, you see a lot in biology. I'm not going to make you memorize any of these. So interesting things with amines. You got nitrogen with a lone pair of electrons. I teach general chemistry students. It's got to be sp3 because I count 1, 2, 3, 4 electron domains. You saw a little weirdness with the aromaticity, sticking this in a ring. Typically there was a double bond there, or sometimes saying it was aromatic when there was some debatability about that. Lone pairs take up more room than bonds. And of course here we have a methyl group taking up even more room. So less than our 109.5 special tetrahedral bond angle. So amines can do interesting things. It says nitrogen can have 3 different groups in a lone pair, but enantiomers cannot be isolated due to inversion around nitrogen. So here's this transition state. Now, of course, here, since I've drawn this flat and planar, this almost looks like a sp2 situation where this is an unused atomic orbital. In fact, they're saying here's an sp3 orbital. Oh, here's a p orbital. Now we're back to an sp3 orbital. So I guess the important things is you don't want to look at this as 1, 2, 3, 4 different groups and call this thing chiral, because inversion can occur. Well, now that we're on to stereochemistry, we do have chiral amines. Probably in that first slide with all the interesting drugs, the amine was on a chiral carbon. And so here we see some chiral amines. And it stems from the chiral carbon. And we don't care about the inversion of what's going on here. Of course, we don't here because we have 2 hydrogens. We can imagine alkyl groups. However, we can have quaternary ammonium salts that are chiral. So this nitrogen has the benzene ring, the isopropyl group, the methyl group, the ethyl group, and hence has chirality. So the same rules, 4 different groups makes it chiral. And inversion is not possible. And so we could have a chloride or nitrate salt, and these things can be bottled up and they will last forever. So here's some more weirdness with nitrogen. Here is R1,2,2-trimethyl. And aren't you glad I said I'm not going to make you learn to name any of those heterocycles, amine-containing heterocycles. We can just read them and get all the benefit we need. We see here mirror images. They're not going to be superimposable. Boy, something I never thought of before. What priority group do I give the double bond? R. I won't make you do any of those and I won't have to explain it. If the nitrogen atom is contained in a small ring, for example, it is prevented from attaining the 120-degree bond angle that facilitates inversion. So this can't pop down like that and that pop up, then it would be that one. Such a compound has a higher activation energy for inversion. The inversion is slow and the enantiomers may be resolved, meaning we can bottle these up, we can separate them. So physical properties of amines. My favorite question. Physical properties follow fill in the blank. Forces. Physical properties follow forces. Intramolecular forces. What are your intermolecular forces? London dispersions, dipole-dipole, and the strongest intermolecular force is hydrogen bonding. Now nitrogen left of oxygen on the periodic table, not as electronegative, so this is going to be a less polar bond than oxygen-hydrogen. The hydrogen bonding is weaker, but still undergoes hydrogen bonding. Here we see hydrogen bonding with the water. So a secondary or primary amine can hydrogen bond with itself. If we have a tertiary amine, there's no hydrogens bonded. So this cannot hydrogen bond with itself, but it can hydrogen bond with water. Tertiary amines cannot hydrogen bond, so they have lower boiling points than primary and secondary amines. All right, for fun and no prizes, since these all have the same molecular weight, what intermolecular force are we holding constant? Don't shake your head, though. I just named them at the beginning. I say if it has electrons, it has this force.
London dispersion.
Yeah, London dispersion. All right, and as things get larger in mass, they have more electrons, they have more London dispersion force. So 5960, 59, 5960. London dispersion force is about constant. So what we can see on this slide is, well, this has dipole, no hydrogen bonding, 0.8 degrees Celsius. That's a gas. Got to buy that in a cylinder. Tertiary amine cannot hydrogen bond with itself. It has a dipole though. Lone pairs up in that pyramidal, triangular pyramidal shape. So, here's an alcohol for comparison. Here's a primary amine. We conclude, well, this probably has more of a dipole moment, but also stronger hydrogen bonder. Boy, I don't want to talk like that. Stronger hydrogen bonding. But all of these have hydrogen bonding going on. None of these have any hydrogen bonding going on. Solubilities. If we have an amine with 6 carbons or less, immiscible of water, soluble in the water. All amines accept hydrogen bonds from water and alcohol. No, not all. Primary and secondary. Oh, yeah. They'll accept all amines, except for the quaternary ammonium salts, can accept hydrogen bonds from water and alcohol. This one, to me, seems counterintuitive. It says branching increases solubility. Here's the most important part of this slide. Most amines smell like rotting fish. Notice these interesting names here. Putrescine, which is butane 1,4-diamine. Cadaverine, penta 1,5-diamine. Where does this come from? Every year I have a student, they want to go to work at the cadaver farm in Alabama or someplace where forensic scientists do their forensic things. Note takers in this class? Interesting side note, didn't do it this semester. Many times I have OChem students isolate caffeine from tea, and at some point they're like, what stinks? I'm all, that's the caffeine. So that lone pair of electrons on nitrogen can act as a base, proton acceptor. So aqueous solutions are basic. Ammonia has a pKb. Got to switch modes from pKa's to pKb's. Of course, if you know this, you can calculate the pKa of the ammonium ion. Alkylamines are usually stronger bases than ammonia. Why is that? We'll find out in the slide. Alky groups are electron donating. Increasing the number of alky groups decreases the solvation ion. So secondary and tertiary amines are similar in basicity. We won't worry about that so much. How about some reactions? As a nucleophile, is this SN1 or SN2? Gotta see who's awake.
SN2.
How do you know? That's very good.
Strong nucleus.
Sounds good to me. I know it's not SN1 because I don't see a carbocation intermediate. It's concerted. Always got to review stuff we've already learned. New carbon-nitrogen bond formed there. I'd rather they said Bronsted-Lowry here, but reaction of amine as a proton acceptor. So most amines are weak bases. What does that mean? That means we have equilibrium involved. So here's our Kb expression. And of course here we see this hydroxide being formed, so we can think of this as a Uranus base. Increases hydroxide concentration when put in water. Amines are strongly basic, and as such they can abstract a proton from water, giving ammonium ion and hydroxide. The equilibrium constant for this reaction is called the base dissociation constant for the amine, symbolized by K sub B. That's why Chem 2 is a prerequisite for this course. Interesting thing here. The pKa of this base here is the pH at which half the molecules are protonated. Sounds like the Henderson-Hasselbalch equation. Sounds like halfway to the endpoint in the titration curve. Sounds like a good idea for figuring out if you're going to do an extraction where you want the pH. We're going to look at that. Not today, but soon. We'll look at half of it today. Alky groups stabilize the ammonium ion, making them stronger bases. This thing donates electrons by induction. So here's just ammonia, pKb 4.74. Here's the methylamine or aminomethane. Smaller pKb value, stronger base. And here's something weird. Here's aniline, and you see that lone pair overlapping with the pi system of electron density. And here's just, could be methylamine like the other page, any delocalization of the electron pair weakens the base, stabilized by overlap. Protonating aniline is more endothermic than protonating this primary amine. This, we want to interpret this. This line's lower because it's more stable before it's done any acid-base chemistry. That's what that statement there is. So how many of you like the aromatic chapter? So we looked at this, how we were able to count these electrons as part of the pi system and get 2, 4, 6. And Huckel's rule says that's aromatic. And I told you I didn't like calling this an sp2 hybridized nitrogen, but it's in a ring and somehow we get to count that. All right, so we get it protonated and we've lost aromaticity. And we say this is non-aromatic. Because this is sp3, we can't say it's anti-aromatic with our 4n and n equaling 1. Now, just for fun, what is the pKb of this base? Do it in your head. What's the negative log of this number? All right, I did it for you. So those other two bases, one was like 4 point something, and then we had 3 point something, 15. So very much less basic. When pyrrole nitrogen is protonated, pyrrole is less aromatic. It loses its aromatic stabilization. Therefore, protonation of nitrogen is unfavorable. So this thing is a very weak base, which, I mean, if you walk in and look at it before the aromatic chapter, you say, oh, there's a lone pair. That should be on par with all those other amines. And this shows us that it's not. Pyridine. 2, 4, 6. I'd have to conclude pyridine is aromatic. Here's piperidine. And all we're looking at is the hybridization. Now, I have no trouble teaching students or telling them that this is sp2 hybridized because I'm going to go 1, 2, 3 electron domains and say they're all stuck in a hybrid orbital and get to the magic number of 3 by mixing 1 s and 2 atomic orbitals. And also, no trouble saying this is sp3 because I'm going to go 1, 2, 3, 4 electron domains and claim that they each have to be in a hybrid orbital. Pyridine is less basic than aliphatic amines, but it is more basic than pyrrole. That thing we just looked at does not lose its aromaticity on protonation. I put a hydrogen on here and put the plus charge. I still get count 2, 4, 6 electrons. And so protonated pyridine is still aromatic. Aromatic amines are generally less basic than aliphatic amines. This is true when the nitrogen atom is part of the aromatic system, as in pyridine, a hybridization effect, and when the nitrogen atom is bonded to the aromatic ring, as in aniline, we have a resonant effect. Let's talk about ammonium salts. So this thing smells like rotten fish, could be water insoluble. This thing doesn't have any smell because it's not very volatile, and now it's very charged. It's water soluble, ionic solids with higher melting points. So this is very non-volatile, soluble in water, and no foul odor. Guess I'm mixing my animals. No fishy odor. Unless that fowl's been dead for a long time. Then we got a putrescine and cadaverine. Now this ought to look like OChem lab. How would we purify an amine? Well, we make use of its acid-base properties. Well, we could just take our amine, dissolve it up in ether, just add some water and shake it up, and some salts might come out into the water, and we can drain the water out. Let's put some water back in, treat it with HCl. So then our acid-base chemistry occurs, and we put the amine in the aqueous layer. Then we can drain this into a beaker for safekeeping, pour the organic layer out, and that's going to remove what other organics that are either acids like benzoic acid or neutral compounds. All right, so we add what we drained out back into the set funnel. Now we add some base. That would pull out any benzoic acid. And of course, we get the chlorine away there. It's all in the aqueous phase. Now we can drain the aqueous phase around and evaporate our ether, and we purify our base. That'll be all for today.